All right, we got a bunch of friction examples to go through here. I got 5 of them, so this might be a longer video than normal. We'll see. Okay, so starting out, we got this first example. 10 kilogram block, it's on a 30-degree ramp, coefficient of static friction of 0.6. How hard do you have to push the block to start sliding down the ramp? Okay, so first of all, this implies it's not going to slide on its own. We can safely assume that. We could check it, but let's just start. Let's assume it's let's check it. We'll check it here. So we've got block right on the slope, and the components of the forces, right? It's on a slope, so we want to draw FG parallel. Oops, that's not it at all. FG perpendicular. Again, I've just already made 2 mistakes. It's not great. We'll see how it goes. Normal force. And let's assume if it's going to check if it's going to slide down that the friction is going to be that way. But let's stop for a moment here first. Just have these 3 forces. So normal force, F net perpendicular equals F normal minus FG perpendicular. I think we can safely say that F normal is equal to FG perpendicular, right? Because this should be 0. F net perpendicular is 0. So normal force is equal to 84.9. Okay? From that, we can get the maximum force of static friction, right? It's going to be normal force times mu s. Coefficient static friction, this is 50.9. Okay. And the force of gravity parallel to the slope is mg sine theta, which is 49 newtons. So with no force acting on it, right? The only 2 forces I guess we can go ahead and say like static friction is pointing that way. Force of gravity parallel is not able to overcome the maximum force of static friction. All right, but let's say we are pushing down. So if we are pushing down, then the F net, I'm going to draw here, right? Then F push, and this is F friction. If we're pushing down, then net force is equals F push plus FG parallel minus the force of friction, right? So this is, let's say MA. Equals force of push plus 49 minus, and we want this to be the FS max. All right, because we want it to just start sliding it down, we have to push it so much that the static friction is overcome, and the maximum it can be is this. So, and again, we can even say here what the acceleration is. We want this acceleration to be just more than 0, just bigger than 0. So let's call it 0. This is the absolute minimum it can be. So FP plus 49 minus 50.9. And the answer for the force push is 1.9 newtons. Okay, what if I'm pushing it up? Go back, we can erase these, right? You're now pushing up the ramp. We want it to start sliding up. So just because we're pushing up doesn't mean it's going to start sliding up. But we want it to start sliding up. So that means that the static friction is going the other way. Right, the force of friction. So now, F net parallel is equal to F push minus FG parallel minus force of friction. Again, this is 0. F push minus 49 minus 50.9. And we get an F push is 99.9 newtons. All right. Now we've got a block sliding 5 meters. It's initially sliding 5 meters per second, and it's going to go up a ramp. Okay, so again, this time we've got same force diagram, basically. But there's only those three forces, right? Because just because something made it slide up this ramp, but it hasn't yet, or it's not pushing on it anymore. Okay, so we can start there. All right, first things first, right? We've got F net perpendicular is Fn minus Fg perpendicular. So far, so good. F net parallel is just equal to negative Fg parallel. I guess I should start being more like that. It's going to be my positive direction. Okay. Now, here's where it gets a little bit... and friction. I don't know how I forgot friction here. Force to kinetic friction. It's going that way, right? Its velocity is this way. So we got a force going back that way. And I'm actually going to redraw this in green because green's going to be my forces. Okay? So my F net parallel is then minus the force to kinetic. I'm all over the place with colors. Minus force to kinetic friction. Okay? So... all right, so this is true. Now, we start getting into this and it gets a little bit, so we have mass times, right, we saw that for the F net parallel, we have mass times a perpendicular, and that's all going to be 0. And that's equal to normal force, right, minus F mg cosine theta. Normal force equals, oh, here's a problem. This doesn't actually say. We have that it is equal to m times 9.8 times cosine of 10. I don't know what the mass is. Huh. Seems like a problem, but let's just keep going just in case. So what if I have F net parallel then is equal to, oh man, I still don't have that mass. It's minus mg sine theta minus normal force times mu k. This is ma is equal to, ma parallel is equal to negative, that we plug that in, it's negative 1.7 times the mass. And you plug this in, 0.4, and you get negative 3.86 times the mass. And lo and behold, the masses cancel out. And so we get the parallel acceleration to be negative 5.56. And now we can do kinematics, right? V final is going to be 0. V initial is going to be 5. And we can treat this as if it's a 1D kinematics problem because it's just going in a straight line, right? And so we use V final squared equals V initial squared plus 2a change in x. And we're going to get a change in x of 2.25 meters. So I didn't give you the mass to this problem, and that turned out to be fine. If the only forces acting on this are gravity, normal force, and friction, mass will not matter. Okay, that's good, right? Think about like if you like going down a slide. Imagine if like different sized kids would have different like speeds going down the slide. Wouldn't that be a problem? Right? You'd have to like calibrate, be like, but like instead at a certain angle, everyone should slide about the same speed. Right? And you can change your force of friction, right, by having different like putting different parts of your body down. Thinking about like if you right, like if you put your shoes down, you're going to slide a lot slower than if you're sliding on like your like shorts. But the reality is like it's still mostly consistent. Okay? The acceleration is going to be dependent on the not on the mass. Right? Third example. So we got this block here. This time it is sitting table here. We've got a force. I'm actually going to make it a little bigger for our purposes. So we got a block. And we have a gravitational force, a normal force, and this pulling force here. And that this is 30 degrees. And I think we can safely say the frictional force is going to go the other way. It's starting at rest, so we know that it's going to oppose that sort of like attempt to move it horizontally. So again, F net perpendicular is equal to normal force plus the pulling force that's perpendicular minus gravity, right? And F net parallel is going to be equal to F pull parallel force of friction. I guess actually, I don't know why I'm using parallel and perpendicular. That just seems silly of me. I'm going to use X and Y because this is a horizontal vertical situation. So you're F net X, pull X, and F net Y, F pull Y. Okay, so F net X, right? Oh, this is actually, sorry, this is Y. Ugh. I am all over the place. X, X. Okay. All right. So this one was pretty easy. Like, this is still 0, right? We're not getting any vertical motion. Or at least we shouldn't be, right? Because how much force would you need to pull this up off the table? 98 newtons, right? At least. That's the vertical force. And we're not pulling anywhere near that hard. So, no worries. This is equal to the normal force, right? Plus F pull sine 30 minus 98. So, the normal force is going to be equal to either, right? It's got to be either 83 in part A or 68 newtons, which means the maximum force of static friction is equal to each of those times 0.6, and those are 49.8 or 40.8. There we go. Okay. Maximum force of static friction. The reason we have to find those is because the first thing we want to do is we want to figure out whether this slides or not. Okay. So, F net X is going to be equal to, well, actually, let's even say here, what is the pulling force? F pull X equals either 26 newtons or I don't think I wrote that down. Huh. All right, let me do that really quickly. Sorry. I should really pause the thing, but I'm not gonna because I'm lazy. So it's gonna be, right, it's gonna be 60 cosine of 30. 52, basically. Or 52. So, in this case right here, that is enough to pull harder than the maximum force of static friction. In which case, in part A, so at the 30 Newton problem, right, this F net X, it's not going to move. So AX equals 0, which means that 0 is equal to F pull X minus the force of friction. The force of friction is then 26 newtons. In the 60 Newton scenario, it moves. So since it moves, right, we have to say, okay, 10 A X is equal to the pull. Guys, I'm doing extra work here that I don't need to do. Apologies. It's gonna move. I didn't ask you what the acceleration was. I was about to all solve the acceleration. Just gonna go off on a tangent. I got it off to the side here. Oh, no. What is happening there? All right, I guess I'm not deleting that. Anyways, so if it doesn't move, then we know that the force of kinetic friction is equal to normal force times UK. And that's a known value, right? We've got 68 times 0.2. And it turns out That value is 13.6. So those are the two answers. Okay, so one of the first things you need to do usually in these problems is check to see whether it slides. Okay, we've done that first in a couple of these problems. So I strongly encourage you check to see if it slides. Okay, getting a little bit more complicated here. Two blocks. They are attached by a rod, so they could be pushing each other or pulling each other. Let's figure out if they're pushing each other or pulling each other first. Okay, so we know that mass shouldn't matter if they're on a ramp and the only forces are friction. So which of these would slide faster? The one that has a higher coefficient of kinetic friction, right? So A is, or lower, A is going to naturally slide faster than B, which means A is going to be pulling B along. So it is going to be a pulling force. All right. So we've got, this is A, we've got FG parallel, FN, FG perpendicular, tension, whatever you want to call it, the rod force, whatever. And for B, we've got tension and FG parallel, FG perpendicular, FN. So what if you got that wrong? What if you guessed the wrong way for the tension? So we guessed that they're pulling each other, like A is pulling B along, but they also could be pushing each other apart. What would happen if you did this is you get a negative answer for tension, which is just fine. It would just tell you that you guessed wrong in the direction. So don't worry too much about guessing what direction it's going to go, because you'll figure it out. You have to figure it out. All right, I'm not going to do the perpendicular direction. At this point, we know that normal force, right, with no other things happening, is just equal to mg cosine theta. So the normal force of A is 17. The normal force of B is 25.5. Right, in the parallel direction, F net A is equal to FG parallel minus T. I'm making this way positive. And F net, my guys, I'm so bad right now. I forgot about the force of friction. Force of kinetic friction is going back. How am I doing this? I'm just all over the place. B equals FG parallel plus tension minus force of friction. Okay, fortunately we can plug everything into these, right? We have, this is 2A equals 2 times 9.8 times sine 30, which is fortunately just 9.8, minus the tension. And this is 17 times 0.2. And this one right here, this is 3A equals 14.7 plus the tension minus, this is, it's not 17, it's a 25.5 times 0.5. And as we've done before in connected object problems, we add these two equations together, leaving us with 5A equals 24.5 minus 8.5 minus 12.75. And you should get an acceleration that is 1.68 or so. I think I rounded slightly differently when I did this math earlier, so that might be very slightly off, but it should be there. Okay. So force in the rod. Then we just go back and we try and find that tension, right? So acceleration is 1.68 meters per second squared. We go right back here into this A equation, right? So we get 3.36 is equal to 9.8 minus the tension minus 8.5. Okay, so 3.36 minus 1.3 equals negative T. Did I do something weird here? Y'all, I'm messed up somehow. This is an 8.5. I did the math bad. That's half of it. All right, we gotta go back a second. This is sorry, this is 3.4. 3.4, and that gets to 1.868. That's correct, but it's not minus 8.5 here. Just wrote it down wrong. Or, well, did it in my head wrong. It's right on my paper. So this is then minus 5.4. Right, which gets us a t is equal to basically 0. Well, 2.04, I guess we can say here, newtons. That's the tension. So not a lot. So again, very much like connected object problems, you just got to include the force, the friction force as well, and do the math right, I guess, is where I almost fell down. All right, last one. Okay, so 2 blocks. They're sitting. One of them's on a ramp, one of them's not. I want to know what the tension in the rope is if they slide or don't slide. So the first thing we got to do is figure out if they slide. So at the 5 kilo, we got block A. It has FG parallel. It has FG perpendicular, normal force, tension, and we can figure out the force of friction is back this way. I don't know if it's static or kinetic yet. All right. And then on block B, we've got normal force, FG, tension, and force of friction. Okay, so again, we can do the parallel directions. F net parallel is equal to, for A, it's equal to FG parallel. I'm making this way positive. FG parallel minus tension minus force of friction on A. And F net parallel B is equal to FG, not FG, just tension minus force of friction B. Now, we're actually not going to add these two equations together yet, but I want you to think about it. FG parallel is pulling A down, and friction and tension are stopping it. Tension is pulling B forward, and friction B is stopping it. So if we did add these two together, we'd essentially have FG parallel minus the force of friction A minus the force of friction B. So basically, gravity has to pull harder than those two frictions can pull in order for it to stop moving. So let's go ahead and find what Fs max A is and what Fs max B is. Okay, this is going to be normal force, right, times coefficient of static friction, which is mg cosine theta times 0.3. And this one is going to be mg cosine theta times 0.8. If you do that actual math out, you get, this is 12.7, and this is 15.8. And then we figure out that FG parallel A, so I should say, FG parallel A, it's the only one parallel, but this is 24.5. So it cannot pull, right, because these two together are greater than that, so it will not move. FG parallel is smaller than Fs max A and Fs max B. All right, so what is the minimum tension in the rope then? So we can go to A here, because A is the one that basically has to be stopped the most, right? So F net equals 0. That's equal to 24.5 minus the tension. And if we want the minimum tension, that means you have to have the maximum force of static friction here. That's Fs max A. And if we do that, we should get the tension is equal to that minus 12.7, which is 11.8 newtons. Whew, that's a lot. All right, stop there.